Okay, so welcome back, everyone. I didn't give the proper reference for the last thing we saw. So to recap, the last thing we saw was a bound on the cubic coupling you can have to a bound state, and that the extremal amplitude saturating this bound can be written in this simple way, which is called CDD pole in the interability literature. And this type of bounds was found in this paper by Pablos, Penedones, Toledo, and Van Ries and Vieira in 2016, which really was the revival of this S-matrix Bootstrap program. And as I think Simon said, sometimes we just rediscover things that people knew in the 60s or 70s. So actually, after or when the paper was about to go out, they discovered a paper without any citation in the 72, which had this analytic expression for the bound. So yeah, sometimes you think you discover something and it was already discovered before, but okay. What I'm gonna explain next, which is how to get these bounds numerically, was another thing put out in this paper, and also the connection to interability was not there. So, okay. I was telling in the last lecture that most of the time we need to do numerics. So these are the only two examples I know how to do analytically. So let's revise our recipe for when you need to do numerical bootstrap. So this is again the recipe for the primal approach. So again, we want to choose a spectrum to be able to know the analytic properties of the amplitude. We want to make an ansatz that has analyticity and crossing built in, but now with a finite number of parameters. So you can do a discretization of the dispersion relation I wrote before. Or I will use something else here because it's what most people use. There are the raw variables. Which is a way into to make this analytic ansatz. So you can write the amplitude as an expansion up to some maximum number n max of an parameters. And you have this expansion in terms of this row variable. I'm using R because row will be something else in the future. That is crossing symmetric. And this row variable basically sends us from the plane to the disk. So the definition is here. We have some square roots with some, I'm sorry, should use the same as parameter S0 that we can choose. From now on, sorry. Also because we're doing numerics and we don't want to write M everywhere, I'm setting the external mass to 1, so everything is measured in units of M. With plus here. So what this variable do is to map the complex plane with the right-hand cut in S to a unit disk in R. This is R equals 1. And this S0 is where the center of the disk is. So, okay, this is not a pole, it's just to say this is where you have 0. So S0 gets mapped to 0 in R. And the physical values of S are here, which get mapped here. So it's basically opening up this cut and sending it to the unit disk. And you have the same for the crossed term. Okay, so that's the raw variable. We have analyticity crossing with some n max number of parameters. And we also need unitarity. So now we need to evaluate with these ansatz at a grid of points, Sj, which is bigger than 4. And finally, you choose what you want to maximize. Subject to this unitarity constraint. So in the exercises, you will see how you can use these ansatz with very few number of parameters to actually reproduce the bounds we saw before. Okay, so let me now go into an example you wouldn't be able to get analytically, or at least I don't know how to. So let's go back to the no bound states case. And now explore a little bit further what the space of allowed amplitudes are, because we only saw one parameter so far, this maximum value for what you can say it's like a quartic effective coupling, just the amplitude at some energy below 4m². So this leaf was studied in this paper by Chen, Fitzpatrick, Karatev. So basically, we want to open up this one parameter bound we had for S of S star. So something you can do is now bound the space of amplitudes in two axes. So you have two parameters. One can be the amplitude at the crossing symmetry point. And at some other points, here I'm just choosing one of them, but okay, the physics doesn't change. And you would get something like this. We will also see it in the exercises, where the allowed amplitudes are inside. This is 1, this is -1, -1, okay, and 1, because this should be true anyway. So before we had free boson and free fermion appearing as special points at the boundary of this allowed region, and they would be these cusps here. Let me call it free minus. So what about the amplitudes that you have here at the boundary? These extremal amplitudes would be given by CDD 0, which is one of them, which is basically 1 over the function I wrote there. So instead of having a pole that we're not allowing because we have no bound states, we can have a 0 in the amplitude. So let me write it down. we have again S for minus S, then some parameter that you vary along the curve here. So it's plus here, no, it's minus here and plus here. So you see you get a 0 instead of a pole. And again, we just did 1 over S, so we have unitarity saturation. So you might ask yourself, is there a theory, an iterable theory that appears here in these bounds? And again, the answer is yes. So if this is 0, okay, it's not very symmetric, but you see it in the exercise sheet. It's supposed to be symmetric. On this side here, the lower bound is saturated by amplitudes in Sinch-Gordon theory. So it's basically taking the sine-Gordon Lagrangian I wrote before and just replacing this parameter beta with I beta. So this beta is related in some non-trivial way to lambda, so it has this property of flipping the signs. And on this side, where you have Sinch-Gordon, if you look at the amplitude in S, you will see 2 zeros, one at lambda and 4 minus lambda squared, I guess. So this is my notation for 0. And starting from free boson, which is just a constant, basically, as you move around here, you see the 0 emerging from the continuum and going towards 2, the crossing symmetric point. So at the crossing symmetric point where these zeros collide, you indeed have S of 2 equals 0. And this is where the amplitude for this theory ends. Now what happens on the other side? So here there is another model called staircase. So this is actually just defined as the analytic continuation of this amplitude here. And what happens there is that these 2 zeros that collided at 2 can go into the complex plane. So they live in this imaginary axis. And notice that we couldn't do this before with the bound states, because the bound states should be, the poles can be only in the real line. So this is a new amplitude if you want. You can put zeros in the upper half plane, that's fine. And why is it called staircase? This is just, it's not crucial for what I'm going to say, but if you're curious, it's because you can define some C function that you can compute through some iterability techniques. And the C function depends on some parameter that for small radius gives you the UV central charge of the theory. And for big radius, it gives you the IR central charge. So it goes from 1 to 0, but it looks like a staircase. And actually, it passes really close to the central charge of the minimal models. So starting from infinity, then okay, and blah, 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 up until Ising model, and then 0 because it's a massive phase. So okay, this is just why it's called staircase. And on the other side, you have minus.
Are there finitely many steps, or are there infinitely many of them?
Sorry, can you repeat?
In the staircase, in the C function plot, are there finitely many steps or infinitely many of them? So as I get to the right side, the triangles, the the staircases get smaller and smaller, or they?
I'm not sure if I'm understanding. So from the amplitude, you just have one stable particle. This is really computing like the energy levels in a cylinder that you can relate to the central charge in the at large or small distances. So it's a different quantity, but it comes from this amplitude.
Yeah, it's just whether there are infinitely many peaks in the right one or not.
Peaks? No, it's really monotonic, monotonically decreasing, but it has this step shape that goes close to the minimal models. And well, actually, it depends on the parameter here. You get these sharp steps only when this goes very far away. Otherwise, it looks more like this.
Okay. Thank you.
Yeah, this is an aside. Doesn't have too much to.
I mean, I think you just answered part of my question from Santi's question, but I mean, can you just again explain like the physics that is described by these lines that you call soft Gordon and staircase? Because I'm not sure if I understand what this is like actually.
Yeah, it's just a function that you can relate to the central charge of the CFTs in the UV and in the IR. I'm not explaining what it is because it's outside the course. It's just to see why it's called staircase. But yeah, it's basically the energy levels for the ground state energy level in finite size. I'm not explaining it, sorry. But yeah, it's not related to what we're saying. It's just why it's called staircase.
Okay, but is the physics no different in the staircase and in the sine Gordon?
Yeah, so if you do sine Gordon, you would never see something like this. You would see just a smooth thing.
Okay, thanks.
Yeah, and I mean for sinh Gordon in this case, you can write the Lagrangian and everything. For the staircase, I don't know Lagrangian, that gives me this amplitude.
So does the C function come from some sort of discretized version of a heat equation or something?
Of the
Like,
what equation?
I mean, kind of reminds me of the C theorem, which actually is related to heat equation or the RG flow equation. And
yeah, so this is also done by Zamological. Yeah, I shouldn't have said this because I don't have time to explain it, but it's something called thermodynamic Bethe ansatz. So for interval theories, you can compute the energy levels on finite size purely from the S matrix. It's something related to interval theories, and indeed it's related to the C function because indeed you have the central charge.
right, but it seems discretized in R. It's not continuous. So
sorry?
It seems discretized in R, like as a.
Yeah, so it's more like this when you really send this to infinity, it's sharp, but otherwise it's really like this.
Oh, I see.
It's still smooth. Okay, I won't say anything more about the surface.
One question. What is the ansatz for the analytic bound?
The ansatz so you can get it numerically using these ansatz. And then what you can do is, for instance, the simplest thing you can do is maximize, say, the amplitude at this point.
Sorry, I just mean the line, the -1 to 1 S star, the analytic case. Yeah, what's the ansatz that they plug in to get that?
You just use an analytic function in the cut plane.
Just any function, or I'm just curious what they used.
You can use this expression, for instance, or a dispersion relation where you don't have the poles. But yeah, you would get the extremal amplitude actually when it's just a constant, which is 1. Okay, so on the other side, we will have the minus, if you flip the amplitude, the sign of the amplitude, minus sinh Gordon, minus staircase. But again, there's no physical model for them. You have the amplitude, but there's no Lagrangian, so that's the only thing you know, the amplitude. And yeah, in the exercises, we will use these ansatz to get the previous two plots we had. Well, this one of the cubic coupling and this leaf as well. So, so far, I've considered a single type of particle. What happens if we make a simple generalization? So if you introduce some global symmetry into the problem. So this will be the next example, something we call the Owen monolith. Okay. If I question, oh, I'm getting, I think this is a Z. Okay, so what if you have this Owen symmetry? Now more than one type of particle that transform to each other with the symmetry. So let's consider theories with an Owen global symmetry, where now these particles carry some index, I, J, K, L, that run from 1 to n, so particles in the vector representation. If you want, you can think of it as a toy model for pions. So now this 2 to 2 amplitude will have some matrix structure with these indices. It's again a function only of the model sign invariant S. But now instead of just one function, we will have 3 because of the different ways in which we can contract these indices. So there are 2 convenient base sets. One in which we do this with the indices, so like the trace, Kronecker delta ij, kl. Then another function for when they do this, il delta jk. And the permutation, delta ik, delta jl. So now we have 3 different functions. And another nice way to write this amplitude is in terms of the irreps. So the reducible representations we can have. In this case, it's the singlet, antisymmetric, and symmetric channels, where you have some projectors into each representation. So, sorry, I, J, K, L, which are, of course, some combinations of these Kronecker deltas. So, unitarity will tell you that in this irrep basis, you have the same condition for each of these 3 functions. The different thing is crossing. So you see, if you look at this amplitude either in this direction or in this other one, you see in these bases that you can relate sigma 1 to sigma 3 and sigma 2 to itself. So sigma 1 of S gets mapped to sigma 3 and 2 to itself. But in this irrep representation, you have some mixing with some matrix here, CIB, that will depend only on the number of flavors you have. So it will be something like 1 over n, minus 1 over n, etc. So now the thing is a bit more complicated. We have 3 functions that talk to each other through crossing. And otherwise, analyticity is the same for each of these representation bases. But we can have now, we can put poles in different representations. So you can put poles in the singlet, but not in the antisymmetric, or do whatever you want. Okay, so it's a quite simple generalization, but as we will see, this already gives you a really rich space of amplitudes and some phenomena that you see in general in symmetry Bootstrap. So now we want to find the space of allowed amplitudes SA. So let's consider the simplest thing, which is no bound states in any representation. So for each of these SAs, you only have the cut plane. And we would like to plot subsections of this space of amplitudes, SA of S, which is infinite because S is a continuous variable. So something we can do to map this space is to maximize this functional. Just linear combinations of the different amplitudes at some point. And if you repeat this for 200,000 NAs, you get a really nice object that we call the monolith. So this monolith is a 3D section of the allowed space of amplitudes. So the axis will be the three different functions we have. Sigma 1, say at 3m squared. Sigma 2 at the same point. Sigma 3. And yeah, tomorrow with the computer, I will show you the 3D object. For now, I'll do a very bad drawing. These are supposed to be some edges, but okay, it's a 3D shape with many edges, and you see there are also some cusps. So what are the theories here inside? So, well, of course, to plot something, you need to fix n, but this is the generic picture you have for n bigger than 2. So the first sort of trivial thing is that you again have free theory. So free boson here, which is the most obvious cusp of this object, and appearing also here, the free fermion. Since we don't have any bound states, we again have this symmetry of just flipping the sign of the amplitude that gives you something allowed as well. So yeah, you have free theory, but then there is another cusp, which is not that obvious, sitting here, which is a non-trivial physical model, which is a nonlinear sigma model. And this is very nice because I don't know if you've heard this story about conformal bootstrap and the Ising model, where they could locate the Ising model at a kink of the bounds. So this is a similar story, but in amplitudes. And it's really nice that you get an actual theory at the cusp. So this nonlinear sigma model, okay, the Lagrangian is just some fields and with norm 1. And the amplitude was bootstrapped by the two homologicals in 78. And written in terms of the rapidity theta, rapidity, which is related to S with this cos squared over 2. It's just that it's easier to write it in this variable. It's very natural for 2D. And it's quite simple. It's just a ratio of 4 gamma functions. Where n appears somewhere, and okay, there are other 3 gamma functions and 4 gamma functions here. And they were able to bootstrap this amplitude because the theory is iterable. So now this Yang-Baxter equation that I drew earlier is not trivial. Before we had just functions, so of course we can multiply them in different orders and it's fine. But now we have these indices. So this is an actual equation that you need to solve. So solving this and some extra input, they were able to bootstrap this amplitude to see this as a non-perturbative amplitude that I can write down one line. It's very nice. Okay, so that's one physical model. Then there is some other interesting point here, which is also iterable, that we call periodic Yang-Baxter. It also solves Yang-Baxter. This is why it's in the name. And the amplitude is again some ratio of gamma functions, but now it's an infinite product of them. And it has the strange property that there is some periodicity in this theta variable. So theta is like log S, more or less. So this is quite strange because it tells you that the amplitude looks periodic in energy. And indeed, even though you can solve these Yang-Baxter equations and bootstrap the amplitude, there is no known theory with it. But you see that it appears at a special point at the boundary of this monolith. It looks like a cusp, but it's not actually a cusp. So that's another interesting thing. And okay, you also have all these, when you can flip the signs of all of these amplitudes. But in general, the amplitudes living here at the boundary, they all saturate unitarity. And this is quite strange and not really physical because we expect that in order to have no particle production, the amplitude should satisfy this Yang-Baxter equation so that the theory is iterable. But they do this, and this is something general you see in the bootstrap. So you basically get what you put in. If you put in just 2 to 2 conditions, then you get just 2 to 2. And if you're trying to maximize some function, then the optimization problem will just make the function as big as it can at the boundary. So here at the cuts. So this is something general that you see also in higher D. So it's true that in this sense, these amplitudes here would be unphysical. However, I would like to say they are close. They are a good approximation to whatever is happening here inside. Why? Because the bounds don't change much if you just add some particle production by hand. And yeah, in general, so how do the functions look like? So for free theory, you have nothing. For this nonlinear sigma model, you have some zeros somewhere inside. And the most generic thing is that you can have a bunch of zeros here close to the physical values. the same on the other side. These zeros are spaced periodically in this theta variable. So this periodicity is actually an emergent feature of all these amplitudes at the boundary. And you can have many more things inside here, also more zeros here. And yeah, I think I didn't say, but these zeros you can think of as resonances, which would be poles in the second sheet. So it's telling you that these theories saturating these ON bounds generically have infinite resonances and have this emergent periodicity. So yeah, what I was saying before is that if you add some particle production by hand, yeah, these zeros can move a little bit, and the amplitude will change slightly, but it's already a good approximation. That's what I would claim. But yeah, this fact that they're periodic in some parametrization of energy is already hinting that probably these amplitudes cannot come from a normal conventional UV fixed point. So yeah, we saw that by a very simple generalization of just adding some global symmetry into the problem, you already get a very rich space of amplitudes with infinite resonances that look periodic, etc. Any question?
So if we include further constraints like from higher point amplitudes, would you expect these corners to be lying inside distinct islands or not?
Yeah, it's a good question. I think, well, first, we don't really know how to do multi-particle bootstrap. So it's more about what you're trying to get. So if you want to really focus on a particular theory, then you can put more constraints that allow you to zoom in into this particular theory. Then, yeah, you could get islands. If I cannot tell you if you add 2 to 4 what happens, I expect, yeah, that this object should shrink somehow, except at the points where I have interability, so everything is consistent. But I cannot tell you how much.
I see.
I would say no, but I haven't done it. I don't know.
I mean, I don't know if it helps to think whether it's possible to continuously deform an S matrix while being strictly physical to connect a theory to the other.
Yeah. Yeah, it's a nice point, because indeed, I should have emphasized that as in the leaf, we could really just follow how these zeros move and you go along this curve. You can do the same here. It's just that it's a very complicated set of infinite product of gamma functions with infinite number of parameters. But okay, you can plot them in many sheets and just see how these poles move, and indeed everything is smooth. So yeah, if you add more particles, you should start getting, these other cuts, and I would expect that some other singularities, or zeros in this case, would appear from there, but it's hard to tell.
Yeah. Thank you.
Yeah, so when you first said that you could recover a nonlinear sigma model on the sort of cusp of this monolith, so one of the methods used to recover this was similar to the conformal bootstrap for the Ising model?
Well, the method is really this recipe, but now with 3 functions that talk to each other through crossing. I was making the analogy with the conformal bootstrap just to say that it's really cool to see some physical theory sitting at a kink of your bounds. It's like, okay, this simple bound is telling you that something special is happening here. It was just an analogy.
Okay, understood. Thank you.
But yeah, the philosophy is the same. Like, you impose some consistency conditions and get some bounds.
if I can also ask a question.
Yeah.
So if I understand, this C matrix is basically like a purely like group theoretic
Yes.
factor from the change of the
Yes.
channel. So do you regard that as some sort of color kinematics duality equation? Because we have some, transformation property on the kinematics under this?
I haven't thought of that. I feel this is like much simpler than that, but I haven't thought of that.
Maybe we can discuss.
Yeah. Okay, so I forgot the time. Let's see. Okay, yeah, the last thing I want to talk about today is this dual approach. So can someone tell me what's not that nice about doing Bootstrap this way with some nmax, finite nmax? So basically, unless I find an analytic expression that is consistent with everything, I cannot tell if these bounds are actually optimal. Why? Because I'm constructing amplitudes that are consistent, but it's just an approximation with an nmax number of parameters. So I actually need to consider the convergence of these bounds with nmax. So for these 2D problems, things are quite fast, but in general, you need to worry about convergence of the bounds. On the other hand, you're actually getting an amplitude that is consistent, so it's a trade-off. But something we figured out how to do is this dual approach, also in the same paper as this, which allows you to put rigorous bounds. So as I was saying now, the primal gives you explicit analytic crossing and unitarity amplitudes. That's very nice. But they are non-rigorous. So in other words, you find some bound, you know this is allowed, and outside it's a maybe. You don't know if you can have theories there or not. So, and you have this nmax dependence. So this is not this. And with the dual, the idea is actually quite simple. So you want to explore this space from the outside and just exclude regions, theory space. And it comes from a simple inequality. So this primal functional we were using before can be bounded by some dual functional that depends on some dual variables k. And this you can think as Lagrange multipliers for the S matrix constraints. So depending on which functional you want to maximize, you would write down a different dual functional that you really need to use these Lagrange multipliers and get rid of the primal variables S. But for some of the simplest bounds I described before, you can just use complex analysis. So I probably need more space. Okay, let's try. So suppose we want to maximize again the value of the amplitude. Say we are in no bound states. Tomorrow we will see how it works for when you have the bound state. And this is the functional we want to maximize, just the amplitude at some point. Then using Cauchy's theorem, you can write it down as some contour integral. And now comes the trick. So you want to introduce some function that puts this pole. So this is using that K has a pole with residue 1 at S star. And then you want to open up this contour. It seems like I'm drawing these sheets in every blackboard. Suppose this is S star. Well, actually, somewhere in the middle. You want to blow up the contour. So if you ask for this dual function to have the same analyticity as S, except for this pole, we need to get this equation. Then you can open up this contour and get the following. So you have the imaginary part, Ks and S of S. So here, what I did was to ask for real analyticity, again, for this dual variable. And also, I need some crossing condition because I didn't write the integral, but I'm basically doubling up the integral I get here from this side. If I put the right crossing condition for K, which is actually with a minus sign, then I can just double up this contour. You can check it yourself. Tuck, tuck, like that. So far, we just have equal signs. Now let's do an inequality. I'm going to say something trivial. This should be less than the absolute value of this. K of S, S of S. So far, so good. But now see that we are evaluating precisely at physical values of the energy. So we can use unitarity to get rid of S. So I'm drawing another inequality because S is bounded in this region. And in this way, I end up with an integral only over K. And this is what I define as the dual function. So you see, it's like almost a trivial thing. And I have this inequality between the primal functional and the dual one. So I know that the maximum of this should be bounded by the minimum of this other function. And the main point I want to emphasize is that this gives you a rigorous bound. And also, oh, I forgot this. It's a bit easier to implement. Well, the implementation is the same, but it's faster numerically because you don't need to impose something like unitarity, which is a quadratic constraint. And at optimality, when you have the equal sign, when you have the optimal bound, you can actually recover the amplitude just from this dual functional. So the amplitude, the optimal one, would be given by this ratio. We have the complex conjugate of this dual function over its absolute value. And this is because you want to follow when you have equal sign here. So if you input, say, this thing here, indeed, you get an equal sign for the absolute value. So this also explains why most of the time you get unitarity saturation. So it's just because you're optimizing something, and the way to get this bound and just close this, it's called duality gap between the primal and dual functional, is to have an equal sign here where you're saturating unitarity. And we will also show in the last exercise how we can get the same bounds for the first two examples. And actually, it's very nice that for the cubic coupling, you can make an ansatz for this function that, again, has some analytic properties that will depend on what you're maximizing. So for instance, here we need this pole. But if you put them with just one parameter, you already get a really nice bound. And it converges really, really fast. So yeah, I think any question? I could stop here. Ten? Oh, okay. Then let's start with the exercises. Did you get the email? Do you have the exercises there right now? Okay. So the first exercise is to see that for 2-2 kinematics in 2D, you get that the sets of in and out momenta are the same. So how would you, for when you have elastic scattering, let's put all of them with the same mass. How would you prove this? The point is from energy momentum conservation. Energy. Mm-hmm.
Because it's the same energy. You can only have that they point the same way or the other way.
Yeah, that's
And they have the same
a
mass.
way to see it. So you can also think of just vectors with a given length, because you have this p squared equals m squared for all of them. And they need to sum to the same thing. But okay, a more brute force way to do it is you can go into the center of mass train. So you set the spatial part. Okay, this is just a number, but I put the vector to be the same. Let's call this P. Let's call this Q. And then from energy conservation, you would have that m squared plus p squared. Well, just twice from particle 1 and 2 should be the same as this. And the solution is that either P is Q or minus Q. Question? Okay. Now for exercise 2, we are supposed to recover this bound for amplitudes where you have no poles. So the trick that I put in the hint is to use a nice variable to go from the cut plane into the disk. So it's similar to this raw variable, but actually doubled. Because of crossing symmetry, we can consider just half of it. And this is in S, this would be in C. And the change of variable that does this is C of S, sorry, cursive, is square root S, form squared minus S, minus S star, so wherever you want to put your S star. Which should look familiar, but you can check this maps this half circle into, sorry, half sheet into the unit disk. So this point 1 is would be infinity. This point here, -1, is 4m squared. The center is wherever you put this S star. And again, the physical values would be here and here. And here. So now what we need to use is this maximum modulus principle. So the main point is that we know this amplitude is bounded at the boundary of the complex plane, or here the disk. We know here it's bounded by 1. Smaller equal. And actually the same here because of real analyticity. So we have an analytic function with no singularities, it's not a singularity, that is bounded in this domain. So there is this theorem in complex analysis which says that if you have an analytic function in some domain, then let's call it F, then its modulus will be maximum at the boundary. And if you have the maximum inside, then F should be a constant. So you see, you can apply this directly to the unit disk. So if you want to maximize anything inside, it should be the same as whatever it can be at the boundary, which is 1. So this bound is saturated precisely by a constant, which is 1 or -1 if you're doing the minimum. Yeah, any question about how this works? Okay, so I'll let you think about the one with the bound state, but it's using the same idea. And I think we can end for today.
Are there any quick questions?
If not, let's reconvene at 4.